It's almost Christmas in London and excitement is in the air. As another night of festivities draws to an end, I fall asleep unaware of the imminent danger.
Hello? Oh, no, Malte. I'll be haunting your dreams tomorrow. Maxime, are you there? Find me all the BPS surface operators in the 62,0 theory. Do it fast.
Okay, so while we wait for the answer, let me take a moment to tell you about the 2,0 theory. Usually we like to define theories by their Lagrangian description, but that's not always possible. And in this case, there's a long history of attempts to try to find a Lagrangian description for the 2,0 theory, and it's still an open question today. So what I'm going to do instead is try to not rely on a Lagrangian description at all, and instead base my discussion on symmetry, geometry, and algebra. For our purposes, the 2,0 theory is a 6-dimensional theory with superconformal symmetry and an SO5R symmetry. The name 2,0 refers to the number of supersymmetries, which can be understood as follows. As usual, the supersymmetry generators transform in the spinor representation of both spacetime and R symmetry algebra. In 6D, because we are in even dimensions, the spinors can be decomposed according to their chirality, and Q is in the chiral representation. This has 4 complex dimensions, and because there are no real spinors in 6D, we count the number of complex dimensions. There is, however, a reality condition that matches Q's by pairs, and it's known as the symplectic Majorana condition. We are left with 2 chiral spinors and 0 antichiral, hence the name 2,0. If we include the supercharges, the full symmetry preserved by the 2,0 theory is called OSP 8/4. It is the algebra presented here. You don't need to memorize this algebra, but it is important to know that from it we can build representations and therefore obtain a lot of information about what are the possible multiplets in the theory. A concrete way to understand the question raised by Nadav is to consider the Abelian theory, which is a theory of a single tensor multiplet. Unlike the non-Abelian theory, here we actually know what is the field content of the theory at least. It contains a 2-form B, which is analogous to a gauge field, a symplectic Majorana fermion psi, and 5 scalars phi. The supersymmetry transformations can be found directly from the algebra by constructing the appropriate representation and are as follows. From these fields, one can construct a half BPS surface operator much in the same way you would construct a BPS Wilson loop, by taking both B and phi and integrating over a plane. Here, this is along x1 and x2. When we take the supersymmetry variation, both B and phi give a gamma matrix acting on epsilon. And because they act on different spaces, we can diagonalize both of them at the same time. They each have eigenvalues plus or minus 1, so the epsilon satisfying this equation are the ones with opposite eigenvalues, which are 8 real spinors or half the supersymmetries. In fact, this equation can be understood purely geometrically as selecting a plane in 6D and a direction in R5, which are the matrices appearing here. Algebraically, each epsilon corresponds to a supersymmetry Q, and one can check that the supercharges selected by this equation generate the 2-dimensional superconformal algebra preserved by the half BPS plane. Therefore, the content of this constraint is really geometric. It specifies the supercharges preserved by a choice of plane, and therefore the same equation also holds in the non-Abelian theory. We are interested in operators that are defined not over a plane, but an arbitrary surface in 6D, with some arbitrary scalar at any point. The question raised by Nadav is then what are the pairs of x and n such that the BPS equation is satisfied. This is our starting point. The answer is... wait, do we have the answer yet? I don't want to hurry you, but we only have 15 minutes. Thanks. What we found are 4 classes of BPS surfaces, which are type R, C, H, and S. Type R gives BPS surfaces defined by an arbitrary curve in R5, type C are holomorphic curves in C3, type H are surfaces in R4, and finally type S are surfaces in S3. Because of the time constraints, in the following I will discuss only type H. Now the reason you might be interested in BPS surfaces is that because we don't know much about the 2,0 theory, having some non-trivial operators that you can calculate exactly gives you a really important handle on the theory. But more importantly, I think the message here is that because these operators sit at the intersection of many different topics, they can be studied in various ways. In the following I want to give you an idea of how these operators, or these surfaces, rely on notions of geometry, why they are supersymmetric, how they are connected to observables of lower dimensional theory, what is their holographic dual, and how to calculate their Val anomaly exactly. To understand the choice of scalar coupling n for type H surfaces, one can first consider surfaces in 3D. Every point of the surface has a tangent plane in R3, which can be uniquely specified by the normal vector, a point on S2. This construction, which gives a map from the surface sigma to S2, is usually called the Gauss map. The Gauss map has a generalization to planes in 4D, where now the image of G is a point in the space of planes. This space can be understood as a homogeneous space, and by the orbit stabilizer theorem, it is given by SO4 quotiented by SO2 cross SO2, which is isomorphic to S2 cross S2, and the spheres correspond respectively to the space of self-dual and anti-self-dual 2 forms. Our choice of n is the image of the Gauss map restricted to the self-dual 2 forms. Another way of understanding n is as the pullback of the hyperkähler structure of R4 on the surface, and this is why we call it type H. To check that the choice of x and n we have leads to supersymmetric operators, we need to check that all the tangent planes over the surface share mutual supersymmetries. A basis is the following. And one can show that there is a single supersymmetry satisfying all the constraints. If we restrict the surfaces to involve fewer tangent planes, then supersymmetry can be enhanced. One example is surfaces in R3, which involve only 3 tangent planes, but more examples are listed in this table. Lagrangian surfaces are surfaces where one component of n is 0, which means that they involve only 4 tangent planes. There's a nice story of how to relate our surfaces to operators of 4D n equal to class S theories, which I can briefly sketch here. Basically, one can place the 2,0 theory on some background manifold R4 times the Riemann surface C and compactify the latter. Now, in order to preserve supersymmetry, one needs to perform a topological twist, which means that along with the non-trivial metric, one also needs to source some background asymmetric current. This is analogous to having both B and phi when we discuss the surface operator in the Abelian theory. And all that is really important for us is that the supercharges preserved by this compactification are the ones satisfying this constraint. It is easy to check that the supersymmetry preserved by type H automatically satisfy it, so our surfaces are also BPS in class S theories. Finally, we can discuss how the BPS surfaces are realized in holography. The ADS-CFT correspondence establishes a dictionary between observables of the 2,0 theory and observables of 11D supergravity on an ADS7 cross S4 background. The metric of the background geometry is the following, where y is the radial direction in R5 and is related to the coordinate of the Poincaré patch of ADS. The ADS-CFT dictionary tells us that surface operators in field theory are dual to M2 branes in supergravity, with the same surface as their boundary. To calculate the expectation value, one therefore needs to solve the equations of motion of the M2 brane for some given boundary conditions and evaluate the classical action. In general, these equations can be complicated and are difficult to solve. This is where supersymmetry comes in. For supersymmetric boundary conditions, we expect the M2 brane to also be supersymmetric in ADS, and this is an important simplification. If we look for minimal volumes preserving a supersymmetry epsilon, then we can construct the tree form phi as follows. This tree form has nice properties, and in the case of type H it defines a G2 structure on ADS5 cross S2. One can use these properties in supersymmetry to show that the M2 brane obey a first-order PDE. This is a huge simplification, and the equations obey local boundary conditions. Trying to solve these equations in some cases is definitely one of our projects for the future. Before we conclude, I want to mention the other types of surfaces that I didn't present here. There's a similar story for them as well, which is summarized in this table. I should say that our analysis was not systematic. What we did instead was try some Ansätze, which we thought that would lead to BPS surfaces. Therefore, this table may not be exhaustive, and it would be interesting to know whether there are more generalization. For instance, we can see here that type S preserves 2 supercharges, so perhaps there is a generalization preserving only 1. Something I didn't mention either is special supersymmetries, which can be analyzed in the same way, and it's listed in this table. So to summarize, we found classes of BPS surfaces with a rich structure, and here I sketched how they are connected with ideas of geometry, supersymmetry, dimensional reduction, and holography. But it's clear that this is not the end of the story. I already mentioned that we want to study more the holographic description, and another interesting direction would be to study the dimensional reduction of these surfaces to 4D, where we do have a Lagrangian description. Thank you for watching the video. I hope you found it interesting, and I'll be happy to discuss more at the end.
Oh, Maxime, very nice work. What inspired you to look at this?